I think Professor Commange's last slide was a perfect transition to the next presentation on how do we go about assessing causality if we have observational data. And with observational studies, we are always concerned about the possibility of unmeasured confounding, that in spite of our efforts to control for covariates that might be related to both our exposure or treatment and also our outcome, we're never sure whether there might be some unknown, unmeasured covariate that affects both and explains the association, so that association is not causal. And sensitivity analysis or bias analysis methods are an approach to try to assess how strong an unmeasured variable would have to be related to both the exposure and the outcome to explain away our results. I've taught these techniques for quite a number of years in required courses at Harvard. I give homeworks on them, but I find year after year, although the students successfully complete the homework assignments, they never use them subsequently. And so I've struggled with this problem, and how do we do this sensitivity analysis well? And when I ask why don't you use these techniques, the responses are often, well, they're difficult to implement in practice, or they're difficult to report, or the journals don't seem to like them, and so I've abandoned it. And so this attempt at introducing a new measure, the E-value, is trying to get around this problem, trying to provide a metric that's easy to compute, easy to report, which I think the journals will like, though we'll see, and that I think is very informative for readers. I should make it clear that I'm not arguing that the E-value replace the P-value. I'm all in favor of P-values and reporting P-values. I don't think they should be discarded from the literature. I am against the 0.05 cutoff as a dichotomization of the P-value, but I think treated as a continuous measure of evidence, I think the P-value is very helpful and important. So the proposal here is not to replace the P-value with the E-value, but to supplement the P-value in observational studies with this E-value measure. So I'll provide a brief introduction to these ideas about sensitivity analysis for unmeasured confounding. I'll talk about a result which allows one to do sensitivity analysis essentially without imposing any assumptions on the nature of the unmeasured confounder, essentially bounds causal effects. That will lead to this E-value measure, which is essentially a measure of how strong an unmeasured confounder would have to be related both to the exposure and the outcome to explain away the results. We'll go through some empirical examples, and then I'll talk about extensions to other scales and make some final concluding remarks. The presentation here is based on a paper that just came out last year in the Annals of Internal Medicine introducing this E-value metric. So the basic context here is that we have some exposure or treatment variable that we call A, but it's not randomized. We're in an observational context. We want to assess its effects on some outcome Y. To do so, we try to control for a bunch of measured covariates C, which we think are common causes of the exposure and the outcome. But with observational data, we never know whether we've controlled for all possible confounders. There might be some unmeasured variable, U, that affects both the exposure and the outcome, and biases our effect estimates. So sensitivity analysis, or bias analysis, as it's sometimes called in the epidemiologic literature, is essentially trying to assess how strong would an unmeasured confounder have to be related both to our exposure and to our outcome for that observed exposure outcome association to be solely due to confounding. How large would those effects have to be? If we have some sense as to the magnitude of the effects of U on A and on our outcome Y, we can also use that to try to form a plausible range of possible values for the true causal effect of the exposure and the outcome. So as an example, and one we'll be turning to later, there have been a large number of observational studies that have suggested that maternal breastfeeding is associated with better infant and maternal outcomes. But there are concerns in many of these studies that this might be confounded by parental socioeconomic status. In the West, at least, there's a strong gradient between socioeconomic status and breastfeeding. Higher SES mothers tend to breastfeed more often. So might the associations we observe just be due to residual confounding by socioeconomic status. Some studies also don't control for maternal smoking, which is correlated with maternal breastfeeding. So again, might these associations also be explained away by smoking? So we'll return to some examples with regard to maternal breastfeeding a little later. The term sensitivity analysis is used in a variety of other contexts to address problems not just of unmeasured confounding, but also measurement error and selection bias. Here, I will be focusing, though, just on the problem of unmeasured confounding. We can talk about those other biases later, perhaps. But here, I'll be focusing on unmeasured confounding. And a relatively early application of this approach was the work by Cornfield and co-authors concerning the association between smoking and lung cancer. And there had been quite a number of very large observational studies suggesting that the two were strongly associated, but skepticism at the time as to whether that association was causal. Rather famously, Sir Ronald Fisher thought that perhaps the association would be explained away by a genetic variant that increased the likelihood of smoking and the likelihood of lung cancer. And what Cornfield and co-authors did is they said, okay, let's suppose there is such a genetic variant that might explain both smoking and lung cancer. How strong would its associations have to be with smoking and lung cancer to explain away that association? And they showed that for a genetic variant to explain that association away, it would have to increase the likelihood of smoking by tenfold and increase the likelihood of lung cancer by tenfold to explain that association away. And effects that large just didn't seem plausible. And we'll go through the logic on how Cornfield got there and also talk about how that logic can, in fact, be generalized. So the logic that Cornfield and co-authors used was if we let RR denote the estimated risk ratio relating the exposure A and outcome Y, possibly conditional on some measured covariate C. And in Cornfield's work, if we let U denote a binary, and we'll come back to that assumption, but a binary unmeasured confounding variable, Cornfield said, well, let's define a couple of parameters. Let's let UA be the risk ratio relating the exposure to the probability of the unmeasured confounder U being present, and let UY be the risk ratio relating U and Y. And the Cornfield conditions are that U could not be entirely responsible for the association between A and Y unless it was the case, these were necessary conditions, that UA is greater than the observed risk ratio and UY is greater than the observed risk ratio. Cornfield showed it for the outcome, and then subsequently it was also shown for the exposure as well. Or sorry, reverse. Cornfield showed it for the exposure. It was subsequently showed for the outcome. So here we have a picture of Sir Ronald Fisher happily smoking away on his pipe, but he had proposed in a letter published in Nature in 1958 that really that whole smoking lung cancer association was due to a genetic variant. There had been studies at the time suggesting pretty large risk ratios relating smoking to lung cancer. One cohort study suggesting a risk ratio as large as 10-fold, confidence interval from 8 to 14. And so what the Cornfield conditions indicated, again, is that for that supposed variant to explain away the association, it would need to be associated with increased risk of lung cancer by at least 10-fold and also tenfold more likely present amongst those who were smoking than not. And that just didn't seem plausible. So it provided strong evidence that some, at least, of that smoking lung cancer association was in fact causal. And so these conditions, I think, are still useful rules of thumb in assessing how strong confounding would have to be to explain away the exposure outcome association. They're closely related to the Bradford-Hill criteria of the strength of the association. The stronger the association, the more confounding is needed to explain it away. And so, again, it can be a useful rule of thumb, but often we want just not how much confounding is needed to explain it away, but if we had a certain amount of confounding, how much would that change our estimates? Maybe we think that tenfold increase in risk is too large because there is some confounding, but how much should we reduce it then? And that's what sensitivity analysis does. So more formally, we're going to denote the adjusted risk ratio for the measured covariate C relating the exposure to the outcome by this expression here, probability of the outcome amongst the exposed conditional unmeasured covariate C versus probability of the outcome on the unexposed conditional unmeasured covariate C. If the covariates suffice to control for confounding, that would also be a causal risk ratio. But if there's some unmeasured covariate U that affects both the exposure and the outcome, then we would need to adjust for U. And what we would want, if we wanted the causal risk ratio conditional on C, is we'd want to standardize by U as well. We don't have data on U, so we can't do this with data. And so what sensitivity analysis does is defines a bias factor, at least one approach to sensitivity analysis, defines a bias factor, which is the ratio between our observed estimate with the measured data controlling only for measured covariate C, and compares that to what would have happened if we had been able to adjust for U as well, sort of the true causal risk ratio. For those who are familiar with counterfactual notation, if we let y subscript a be the potential outcome or counterfactual outcome, if possibly contrary to fact, a were set to little a, so we have y1, what would have happened with the exposure, y0, what would have happened without the exposure. Then if the effect of the exposure on the outcome is unconfounded conditional on the measured covariate C. In other words, if conditional on the measured covariate C, the groups actually having the exposure and not having the exposure are comparable to one another in their counterfactual outcomes and what would have happened with or without the exposure, then this first expression is just the causal risk ratio. But if we also needed U to control for confounding, then this second expression would be the causal risk ratio, and the first expression would be biased for the causal risk ratio, because we haven't adjusted for C. But none of the development here requires this counterfactual notation. All of the development is really just a comparison of what we observe when we adjust just for the measured covariate C versus what we would have observed for the risk ratio had we been able to adjust for, standardize by U as well. And what many sensitivity analysis techniques do is they express this bias factor in terms of typically two or more parameters relating the association between U and the exposure and U and the outcome. So we'll go through that. And there are many techniques that exist out there. Again, different parameterizations, but essentially the different parameterizations correspond to an effect of U on the exposure, an effect of U on the outcome, and that bias factor is related to those parameters. We specify the sensitivity analysis parameters, we calculate the bias factor, and then we can get a corrected estimate. That's the logic, and we'll walk through an example of this. And again, there are many techniques available, but many of them make simplifying assumptions to get easy to use formulas. One very common assumption is that unmeasured confounder is binary. Another common assumption is that there's no interaction between the exposure and the unmeasured confounder in the effects on their outcome, that the unmeasured confounder has the same effect on the outcome for both the exposed and the unexposed. And that often leads to much simpler formulas. And almost all techniques also assume that there's only one unmeasured confounder. But how do we know? Maybe there are several. So sometimes these techniques are criticized because they make assumptions to assess assumptions. And if that's the case, then what have we really gained? Do we then need to do sensitivity analysis for the assumptions we're making for the sensitivity analysis technique itself? So sometimes these techniques are criticized on these grounds. Some techniques don't require these assumptions, but then require specifying a very large number of sensitivity analysis parameters and become difficult to use in practice. Other techniques don't make these assumptions, but then make no reference to unmeasured confounders at all, just specify the bias directly. But here I'll be providing a technique which essentially relaxes all of these assumptions. And somewhat surprisingly, we can still make progress. So I'm going to define two parameters again, one corresponding to the effect of U on the outcome and the other corresponding to the effect of U on the exposure. We don't know what these are in practice because we don't have data on U, but if we're willing to specify them, we can see how much our estimate might change. We could then change the parameters to see if more bias would even more substantially change the effect estimate, or how much bias we would need to completely get rid of our estimate. So I'm going to define two parameters. The first, RRUY, is going to look at the maximum effect of U on Y amongst the unexposed, comparing any two categories of U. What's the maximum risk ratio that any change in U could have on the risk ratio scale and the outcome for the unexposed? Then we're going to ask what's the maximum effect U could have on the outcome Y amongst the exposed? And then we're going to take the maximum of those two. So it's kind of a maximum over maxima. What's the largest effect that U could have on the outcome Y on the risk ratio scale for either the exposed or the unexposed? Is it a twofold increase or a threefold increase or a fourfold increase in the outcome? How large can the effect of U on Y be? That's our first parameter. Our second parameter is comparing any particular value of U. How much more likely is that value to be amongst the exposed and the unexposed? So if U is binary, then this is just an ordinary risk ratio. How much more likely is U amongst the exposed and the unexposed? Is it twofold more likely, or threefold more likely, or fourfold more likely? But if U is categorical, we can ask that same question for each possible level of U. Maybe U has 6 levels, and we can ask, for U being level 6, how much more likely is it to be level 6 amongst the exposed and the unexposed? What about level 5? What about level 4? What about level 3? And we take the maximum of those risk ratios. Again, if U is just binary, this is a regular risk ratio. Both of these parameters are conditional on measured covariate C as well, so this is essentially the residual confounding having already adjusted for the measured covariate C. How likely is it that U could increase Y having already adjusted for our measured covariate? So this is picking up confounding above and beyond our measured covariates. If in the example of maternal breastfeeding and child health, if we were worried about unmeasured confounding by socioeconomic status and hadn't controlled for income, but if we had controlled for wealth and home ownership and occupation, we might not think income generates all that much additional bias because we've controlled for 3 other markers as well. So these parameters are picking up the residual confounding, having already adjusted for the measured covariates. Once we've specified these two parameters, again, the first one is the maximum effect of U on Y, and the second one is the maximum risk ratio relating the exposure to any category of U, one can show without any further assumptions that the most bias that can be generated on the ratio scale is given by this formula here, which is pretty straightforward. It's just the product of those two parameters divided by their sum minus 1. So if we thought U could increase the outcome at most by 3-fold, and that U is at most 2-fold more likely amongst the exposed than the unexposed, then we would have 3 times 2, that's 6, divided by 3 plus 2, that's 5 minus 1, that's 4, 6 over 4, 1.5. The most such an unmeasured confounder could change our estimate up or down would be by a factor of 1.5. It is impossible for such an unmeasured confounder to generate more bias. It might not generate that much bias, but that's the most bias that could be generated. The bound is sharp, insofar as one can always construct an unmeasured confounder that achieves the bound, but whether the actual unmeasured confounder does, one doesn't know. But again, this is the most bias that could possibly be generated. So it's pretty easy to use in practice. We get our estimate, we get a confidence interval, we specify these two parameters, calculate the bias factor, and then we just divide our estimate and its confidence interval by the bias factor to get the most that such an unmeasured confounder could shift our estimates. So if we go back to that smoking lung cancer example, Cornfield said that, well, he showed that a necessary condition for an unmeasured confounder to explain away the smoking lung cancer association was that those two parameters were greater than 10.7. But let's suppose we did have a genetic variant, an unmeasured confounder that increased the likelihood of smoking by 10-fold and the likelihood of lung cancer by 10-fold. If we plug those into the formula, 10.7 times 10.7 divided by 10.7 plus 10.7 minus 1, we actually get a bias factor of only 5.6. If we had take our observed estimate and its confidence interval and divide it by 5.6, we get an adjusted risk ratio of 1.9, confidence interval to 1.4 to 2.5. So actually, even this amount of unmeasured confounding cannot explain away the observed smoking lung cancer association. We'd still be left with a risk ratio. Even if we had confounding this strong, we'd still be left with a risk ratio, causal risk ratio of 2-fold, smoking increasing the likelihood of lung cancer by 2-fold. So it turned out that Cornfield conditions, one can do better than them. One can do better because the Cornfield conditions consider these parameters only one at a time, whereas this bias factor is considering them jointly. If we let one of the parameters go to infinity, what we actually recover are the Cornfield conditions. So by taking them both into account at the same time, we can not only relax the Cornfield assumptions, because we're not assuming a binary unmeasured confounder, but we can improve on them by considering them together. So we might, of course, think, well, risk ratios of 10-fold of a variant on smoking and on lung cancer just seem too large. What if we specified more plausible values? What if we thought genetic variant increased the likelihood of lung cancer by 2-fold and was 3-fold more likely amongst smokers than non-smokers? If we plugged 2 and 3 and 2 and 3 into the formula, we would get out a bias factor of 1.5. We would take our estimate, divide it by 1.5 to get a corrected risk ratio of 7.1, divide the confidence interval by 1.5 to get a confidence interval 5 to 9.5. So even confounding of this magnitude could at most shift that risk ratio down to 7.1. So it's pretty easy to use in practice. We just specify the two parameters, calculate the bias factor, and divide our observed estimate by the bias factor. But the question's often posed, well, how do we come up with these numbers? We don't know you. We haven't measured you. We seem to be pulling them out of thin air. How do we specify them? And if we just make them up, then there's temptation for the investigator to choose values which make their effect estimate look good. And so the objection is sometimes made that there's too much subjectivity in this sensitivity analysis approach. We don't know what the sensitivity analysis parameters are. We just make them up. If people choose them so that their effect estimate looks good, what do we really gain? And I think that's an important objection. But there are different ways to try to address this, to more objectively ground a sensitivity analysis. One is to report how large would they have to be to completely explain away the estimate, or to shift the confidence interval to include the null. So then the game changes. We're not trying to play with the parameters to make our effect estimate look good. We're trying to get them sufficiently large so the effect goes away entirely. And then we can let the reader decide whether they think that amount of unmeasured confounding is plausible or not. So that's one approach. Second approach would be to create a big table of values with lots of sensitivity analysis parameter values. Could put the relationship between the exposure and the outcome on one axis, the relationship between the unmeasured confounder and the exposure on the other, and get a range of corrected estimates, and again, let the reader decide what they think is plausible. A third approach that can be helpful is to go through the measured confounders one by one, omit them one by one, see which of the measured confounders generates the most bias, what the sensitivity analysis parameters are for that measured confounder, and then ask if we had an unmeasured confounder that was as important as our most important measured confounder, would that suffice to explain away the observed estimate? If not, then we can at least say for an unmeasured confounder to completely explain away our observed exposure outcome association, it would have to be more important than our most important measured confounder. And that can sometimes be a fairly convincing argument. How convincing depends on how good that initial set of measured confounders are. If we've controlled for everything we can possibly think of, it might be quite convincing. But if our initial set of confounders is poor, it might not be a strong argument. And finally, one could use external data or expert opinion to try to inform the sensitivity analysis parameters. Talk to experts, see how large they think it is, or if other studies have measured that confounder, you could use that other data to try to get some sense as to how large the sensitivity analysis parameters are. So what's used, I think, depends in part on the context. Epidemiologic journals are often quite happy to have a table for sensitivity analysis with many values. But it's quite difficult, I've found, to do something like that with clinical journals. But I think at the very least, and this is the approach I'll be focusing on the rest of this presentation, we can take the first approach. Report two pieces of information. How large would the parameters have to be to explain away the estimate? And how large would the parameters have to be to shift the confidence interval to include the null? And I think if we provided that sort of information, the reader would have a much better sense as to how robust associations are to unmeasured confounding. And that's what's going to motivate and even define this metric of the e-value. So for the rest of the presentation, we'll be focusing on this first approach. So the e-value is defined as the minimum strength of association on the risk ratio scale that an unmeasured confounder would need to have with both the exposure and the outcome, conditional on the measured covariates to fully explain away a specific exposure outcome association. The name e-value comes from its being a measure pertaining to the evidence for causality itself. And it's, in fact, on the risk ratio scale, very, very easy to compute. If we have an observed risk ratio of magnitude RR, then one can show that if both of our sensitivity analysis parameters are greater than this quantity here, the risk ratio plus the square root of the risk ratio times the risk ratio minus 1, then that could suffice to explain away the observed exposure outcome association, but weaker confounding could not, where the strength of the confounding is defined by the magnitude of the bias factor. And so this quantity here for risk ratios we're calling the e-value. This is the minimum strength of association on the risk ratio scale that an unmeasured confounder would need to have with both the exposure and the outcome above and beyond the measured covariates to fully explain away our association. The formula is applicable for risk ratios greater than 1. If the risk ratio is less than 1, then you take an inverse first and then apply the formula. And we can apply it both to the observed estimate, and then we can apply the same formula to the limit of the confidence interval that's closest to the null to look at how much unmeasured confounding would be needed to explain away the confidence interval, to shift it to include the null. The e-value will always be between 1, therefore, and infinity. So it's a continuous measure. The larger the e-value, the more unmeasured confounding would be needed. So if we apply it to the smoking lung cancer example, risk ratio of 10.7, 10.7 plus the square root of 10.7 times 10.7 minus 1, what we get out is that e-value for the estimate is 20.9. If we apply it to the limit of the confidence interval closest to the null 8 plus the square root of 8 times 7, we get an e-value for the confidence interval of 15.5. So we could then make statements like, with an observed risk ratio of 10.7, an unmeasured confounder that was associated with both the outcome and the exposure by a risk ratio of 20.9-fold each, above and beyond the measured confounders, could explain away the estimate, but weaker confounding could not. So we really need very substantial confounding to explain away that smoking lung cancer association. We'll come back to examples with less extreme risk ratios, but sort of the generalization of that Cornfield procedure suggests that even more substantial confounding is needed. So that's what the e-value is, and the proposal is always to report the e-value for both the estimate and for the confidence interval. It can be done very easily, and it can be reported very easily as well. We can do something more sophisticated. We can, for example, plot all the values of the two parameters, which would suffice to explain away the observed estimate. So if one of them were, say, a little bit less than 20.9, if one of them were only 18, then the other one would have to be 30 or something of the sort. So we could plot all the values that suffice to explain away the estimate, all the values that suffice to shift the confidence interval to the null. But if we just want that single numeric summary, the e-value, I think, can be a very helpful measure. OK, so let's look at some less extreme examples relating breastfeeding to subsequent maternal and child health. Again, the concern here is potential unmeasured confounding by socioeconomic status. These come from a report from the Agency for Health Research and Quality that had summarized in 2007 the existing research on maternal breastfeeding and child and maternal health, and found that maternal breastfeeding was associated with considerably lower rates of lower respiratory tract infection for an infant, nearly 4-fold lower, risk ratio of 0.28, lower maternal ovarian cancer, risk ratio of 0.5, lower childhood leukemia, risk ratio of 0.81, confidence intervals all bounded away from 1 fairly substantially. So if we were to look at, say, the e-value for lower respiratory tract infection, we could do that for the estimate and also for the limit of the confidence interval closest to the null. If we apply the formula to the estimate, we have a protective risk ratio. So we first take the inverse, 1 over 0.28, 3.57. We plug it into the formula, and we get 6.6. The e-value for the estimate is 6.6. We do the same for the limit of the confidence interval closest to the null. That's 0.54. 1 over 0.54 is 1.8. Plug that into the formula, 1.8 plus the square root of 1.8 times 1.8 minus 1. We get an e-value for the confidence interval of 3.1. So to explain away the estimate, an unmeasured confounder would have to be associated with 6.6-fold greater, less likelihood of lower respiratory tract infection, and have to be 6.6 times more common amongst those breastfeeding than not. So pretty substantial confounding would be required to explain away the estimate and even the confidence interval. We really don't observe risk ratios of 3-fold very much in our epidemiologic research. Moreover, this is the risk ratio would have to have with both the outcome and the exposure, both breastfeeding and lower respiratory tract infection, above and beyond the measured covariate. So pretty strong confounding would be needed there. But we could do this with each of the estimates for the different outcomes. So with maternal ovarian cancer, the amount of confounding that's needed for the estimate and for the confidence interval is still pretty substantial, not quite as large, but still pretty substantial. But with childhood leukemia, we're now getting an e-value for the estimate of 1.7, an e-value for the confidence interval of 1.4. This is now in the range of risk ratios which we pretty routinely see in epidemiologic research. So only more modest confounding would be needed to explain away the relationship with childhood leukemia. That doesn't mean that there's not an effect, just because some unmeasured confounding would suffice to explain it away. It doesn't mean that there's not an effect, just that we should be somewhat more cautious in definitively drawing conclusions from that particular study. So I'd say we have very strong evidence for an effect on lower respiratory tract infection. Even though this is observational data, the evidence seems very compelling. Moderately strong evidence for an effect on maternal ovarian cancer, and maybe only modest evidence for childhood leukemia. There we would want to be somewhat more cautious. So again, the proposal is that this always be reported for the estimate and for the limit of the confidence interval. as well. And I think this would allow for better assessment of causality. And it's a different measure than the p-value. I'm not proposing that we discard the p-value, but supplement it. So the p-value gives measure of evidence that the two are associated. The e-value is a measure related to whether that association is in fact causal. And the two can diverge. So in the maternal ovarian cancer, we had a larger e-value than with childhood leukemia. But the p-value for childhood leukemia is actually more extreme than the p-value for ovarian cancer. They're both pretty low, but the p-value for childhood leukemia is more extreme, even though it has a lesser e-value. Why is that? Well, if we actually look at the confidence intervals, for childhood leukemia, we have a pretty tight confidence interval around our estimate. The confidence interval for maternal ovarian cancer is larger. And so the p-value is more extreme for childhood leukemia, but the e-value is more related to the magnitude of the estimate. So although we have a lot more uncertainty, much larger standard error, not as extreme p-value for maternal ovarian cancer, that limit of the confidence interval is still farther from 1 than it was with childhood leukemia. So again, these measures can diverge. Here we would have stronger evidence for an association with childhood leukemia, but stronger evidence that that association was in fact causal for maternal ovarian cancer. So the p-value can always be made larger and larger for any non-null association by just increasing the sample size. But the e-value cannot. The e-value will eventually converge to the value corresponding to the true observed but confounded association between the exposure and the outcome. In a different context, Rosenbaum calls this the design sensitivity, that limit. But arguably, what's most relevant is not what happens when the sample size goes to infinity, but how much evidence do we have with the data that we are actually using. And that's what the e-value provides. So again, easy to calculate. You get your risk ratio, you plug it in that formula, and you're done. And easy to report as well. You can pretty much just copy and paste the text here. With an observed risk ratio of 0.28, an unmeasured confounder that was associated with both the outcome and the exposure or treatment by a risk ratio of 6.6-fold each, above and beyond the measured covariates, could explain away the estimate, but weaker confounding could not. To move the confidence interval to include the null, an unmeasured confounder that was associated with the outcome and treatment or exposure by a risk ratio of 3.1-fold each could do so, but weaker confounding could not. So again, could just take up 2 lines in the results section. So easy to include even in clinical papers. There are a few important caveats in sort of understanding the interpretation of these e-values. The first is, as I noted earlier, what constitutes a large e-value does depend on how good the initial confounding control is. The e-value is measuring how much unmeasured confounding is needed above and beyond the measured covariates to explain away the observed association. So if we hadn't controlled for income, but we had controlled for wealth and occupation and home ownership, we might not expect income to generate all that much unmeasured confounding. And so even a modest e-value might constitute fairly strong evidence. Whereas if we hadn't controlled for any of those, and we were worried about unmeasured confounding, then even a large e-value might not be all that much evidence because we might think the residual confounding is still quite strong. So this is always relative to the set of initial measured confounders. What constitutes a large e-value is also going to be relative to the outcome and the exposure. We can ask questions like, for our outcome under study, what sorts of associations do we typically see? So an e-value of 2 for all-cause mortality might constitute pretty strong evidence for a causal effect. We know a few, but we don't know all that many exposures that increase the likelihood of all-cause mortality by 2-fold over a 10-year follow-up, say. But if we switch the outcome to suicide, an e-value of 2 might not be all that much evidence because there are a lot of risk factors that increase the likelihood of suicide by 2-fold or more. So again, this is always also going to be relative to the outcome and exposure under study. Should also be remembered that the e-value is conservative. It's providing a measure relating to the maximum bias that could be generated by such an unmeasured confounder. But an unmeasured confounder with those parameters wouldn't necessarily generate that degree of bias. If we have an unmeasured confounder that increases both the outcome by twofold and is twofold more likely amongst the exposed, that bias factor calculation is the most bias that could be generated. But the actual unmeasured confounder may not generate that magnitude of bias. A very rare unmeasured confounder generally won't provide that much bias. So again, the e-value is conservative, but arguably, if what we want is the strongest possible evidence for causality, then we want a conservative measure. We want one that's not making assumptions on the nature of the unmeasured confounder or on its prevalence. So that if, after we've controlled for a bunch of measured covariates, we still have a large e-value, that constitutes, I think, very strong evidence for causality. But we can't really use the e-value in the same way to argue for the absence of an effect because this e-value is conservative. So what we can say is from the study, we don't really have much evidence one way or another. But what we really can't say using this e-value approach is that we have strong evidence that there is no effect whatsoever. A small effect or a zero effect really can only be firmly established, I think, in a very large randomized trial. So absence of evidence, again, is not equivalent to the evidence of absence for an effect. What one can do, and I won't be going through this here, but there are more details in the paper, is one can calculate non-null e-values. If you get an estimate that's very small, risk ratio of 1.3, but you're worried that the confounding's in the reverse direction, 1.03, but you're worried that the confounding is in the reverse direction, you can ask how much confounding would be needed to shift it to any other value, to a risk ratio of 1.5 or a risk ratio of 1.2. So you don't need to only ask how much confounding is needed to shift it to the null. You could look at other values as well. Same approach can pretty much be used without change for odds ratios with a rare outcome, for hazards ratios with a rare outcome at the end of follow-up, for ratios of count outcomes, or for ratios of continuous positive outcomes. One just replaces the risk ratios with hazards ratios or odds ratios and uses the same formula. With odds ratios with a common outcome, one cannot apply the formula directly. It is not applicable. It will exaggerate the amount of confounding that's needed, but one can still, in that case, get approximate e-values using a square root transformation of the odds ratio. And I've shown recently that that square root transformation of the odds ratio, if the outcome probabilities are between 20% and 80%, will be within 25% of the true risk ratio. The odds ratio itself can be exaggerated by a factor of up to fourfold, 400%. For the risk ratio without that transformation, but with that transformation, you'll be within 25% of the risk ratio. So one could take the square root of the odds ratio and then get an approximate e-value by applying that approximate risk ratio into the e-value formula. I've recently shown that that transformation is in fact minimax for the minimax transformation for the risk ratio itself. And there are other formulas for hazards ratios with an outcome that's common at the end of follow-up. One can likewise, with a continuous outcome, if one's looking at differences in a continuous outcome, one can get approximate e-values using some of the conversions in the meta-analysis literature, flipping between standardized effect sizes, odds ratios, and risk ratios. So with a standardized effect size of magnitude d, which is obtained by sort of having the outcome variable divided by its standard deviation. And if the standard error for that standardized effect size is SD, then you can get an approximate risk ratio with this conversion formula here, approximate confidence interval using that standardized effect size and its standard error using this formula here, and then once again get an approximate e-value using that e-value formula. These are now approximations. They're relying on assumptions, unlike the e-value formula for risk ratios, but it's helpful insofar as then we're moving to a standardized scale. There are other sensitivity analysis techniques for continuous outcomes or for odds ratios with a common outcome. Those typically do impose additional assumptions as well. I think some of them can be useful. Also, but if we want this e-value, at least we can get an approximate e-value regardless of the scale that we're using. So going back to the points I had made at the beginning, why people don't use sensitivity analysis, it's hard to do, it's hard to report, it's hard to publish. I think this e-value approach has a number of advantages. It's easy to compute. You can do this by hand with those simple formulas. If you don't even want to do it by hand, we have an online e-value calculator. You just put in your estimate, put in the confidence interval, and indicate the effect scale, and it does all the computations for you, produces an e-value for the estimate and the confidence interval. We also have an R package, which will do this also. So it's easy to compute. It's easy to report. Again, you can pretty much just copy and paste those 2 lines into your clinical paper. It's easy to interpret. Readers find it fairly intuitive. It provides a standardized metric across different effect scales. At least with the risk ratio scale, it can be effectively calculated and computed without assumptions. We're not imposing any assumptions on the nature of the unmeasured confounder. It removes subjectivity and sensitivity analysis, and it moves away from using sensitivity analysis parameters that are defined on the odds ratio scale, which I tend to think have been used frequently in the past, but exaggerate the amount of confounding needed because they're typically interpreted as risk ratios, and with a common outcome, they don't have that interpretation. So for all of these reasons, I think the e-value is a helpful approach. I think one setting to avoid this e-value approach is when you have an unmeasured confounder, you know what it is, and you know that it's rare. And then the e-value is just going to be too conservative. An unmeasured confounder won't generate all that. That's very rare, won't generate all that much bias. There are other formulas that can be used and I think are probably preferable if you know what the unmeasured confounder is and you know that it's rare. But otherwise, I think this can be a very general approach to assess robustness to unmeasured confounding. So in conclusion, we've seen that sensitivity analysis techniques, I think, are a very helpful tool to assess sensitivity or robustness to potential unmeasured confounding. This is a problem in all observational studies. I think it needs to be taken more seriously. Too often epidemiology is criticized for having a result one day and then the next week another study that seems to contradict it. And I think if we took more seriously this issue of unmeasured confounding and how robust our conclusions are to it and how strong our evidence for causality really is, I think this would in part help address that problem. We can use this e-value approach to assess the minimum amount of unmeasured confounding needed to explain away the association. If we have an e-value that suggests the evidence is quite robust, then I think it can be a very strong argument, especially if we've already controlled for a rich set of measured covariates. Again, it is more difficult to provide evidence that an effect is absent, but for establishing that an effect is present and that it's causal, I think these e-value approaches can be useful. I think too many of our practices from observational studies have been inherited from randomized trials. The p-value in a randomized trial, provided there aren't other complications, does provide a measure of evidence for causality. But in an observational study, our central threat to causal inference is often not statistical uncertainty, but unmeasured confounding. And the e-value approach addresses that. It can, again, be used for at least approximately for all different effect measures, so provides a standardized scale. I think it could be used broadly. If it is used, I think our inferences about causation will be on much firmer ground. It's easy to do. Whether this catches on or not depends in part on the interest of all of you. I think it's already been employed in 50 published papers since its introduction about 8 months ago. So I'm hoping that it does catch on and that our inferences, again, in biomedical and social sciences about causation are more firmly established. Thank you.